myself Deepak Maurya. In this video lecture, I am going to explain you the uniaxial tensile test. The first question arises, why do we need the uniaxial testing? So whenever we are going to design any machine component or the machine, we should know where it is going to fail, the which position it is actually going to fail, and at what the maximum load it can sustain. So for that we need the uniaxial testing for a particular material. Okay. But in actual condition, the component is not subjected to uniaxial loading. First we should see, what is uniaxial loading. This is the sample what I am creating here, drawing here. This is its cross-sectional area. Okay, when this sample is subjected by a force F in one direction only, so that is a uniaxial loading. In this case, we are doing the testing. But in real cases, this is not the case. In real cases, if you will see this excavator and just if you will see that here the teeth, is it when it will be go and do perform its work, it is not uniaxially loaded. It will force it here. It is having the two component. Okay, just I am separating the forces, or I am just breaking the forces. So at this point, the point of the state, at this point, the state of stress having the normal as well as the shear. In normal also it's not necessary just only in one plane. It may have the different planes. Okay. So at a point it is a biaxial or multi-axial loading. Okay. But we are doing the testing in the uniaxial direction. Why? Because we will convert this uniaxial testing in with the help of the failure theory into a biaxial or multi-axial loading conditions. Okay, so like this we can sort out. So here when we are applying the force and this is the cross-sectional area, we know the stress is equals to force by of cross-sectional area. This is the area of cross-section, and I am again showing this cross-section. This is the width W or B, and this is the thickness T. Okay, so this area will be force by of width into of thickness. Okay, so we are doing the uniaxial test to find the ultimate tensile strength, or the position where or the maximum load at which it will get break or fail, input and the output of the machine. So with the help of the load cell, we are measuring the load, and the crosshead displacement give us the displacement. So load cell is providing us the force, and the crosshead displacement is providing us the displacement or the elongation. Crosshead displacement, we will see crosshead displacement. Crosshead will give us the displacement. So from there, so we are actually providing the crosshead movement, okay, or the position rate at which this crosshead should move. Due to that movement, the load cell will feel the force and it will capture the force. So we are getting the force and displacement, that is the elongation from the machine data. Okay, and we will get the values, maybe any curve. This is some bit tactile material curve. Okay, so we can get different curves. There I am not going. So we are getting the force versus displacement. Okay, we know if the higher the cross section area, more the force will be there. So I'm not interested in the force versus displacement. I am interested in stress versus strain. Why? Actually, we are converting these terms into a terms which is more useful. This force by cross-sectional area. This quantity give me the stress. Similarly, displacement divided by the total length give us the strain. So we are interested in stress versus strain because that is the directly the material property instead of force versus displacement, because this will depends on the length and the area of the specimen. Okay, what will actually happen? I'm just going to show you the drawing. If this is the specimen of having the width B and having the thickness T, okay, and having the thickness T, this is the cross section area. So if this cross sectional area will be more, we need the higher force. So we don't require that things. We want a directly dependent on the material property. So material property is a stress. Okay, that is force by area. So we are getting this force directly from the load cell and this displacement directly from the cross-head movement. So this force is accurate because that we are measuring with the load cell. But what about this displacement? Is it a correct? Because from this stress strain curve, we are going another material property that we are called the modulus of elasticity. That is the slope of this curve. That is sigma by of strain. That is E is equals to sigma by of strain. That is the slope. If this displacement is wrong or having any other value, or this modulus of elasticity will be different. So we should be sure that this delta must be correct. So my question is it correct? So it is not a correct. Not correct if we are using the cross-site display. If we are measuring the cross-site displacement. Okay. Why it is not correct? For understanding that part, we are coming to here. Actually, UTM are of two types. That is the screw driven and the hydraulic driven. Okay, this is a BIS company UTM. It is having the hydraulic driven. Okay, so this either one of the jaw is fixed and another one will move. Okay, so while moving upward, when we are providing the hydraulic force, it may have some play between the uh, crosshead and the movements. Similarly, here this is the screw driven UTM. So this crosshead, actually this we are always saying this part is the crosshead which is having the load cell here. Okay, that you will understand from here. This is having the load cell here. Okay, this is part we call the crosshead, and this crosshead is moving here. There are the screws on which it will move. Okay, so if there will be some play either due to the screw or here in due to the hydraulics, okay, this will not give us the correct displacement. Okay, avoid that part. Otherwise, we will not get the correct E. If we want the correct stress, we will get the correct stress by using the load cell. Okay, we will get the correct by using the load cell. But this del is not correct by using only this cross-site displacement. This cross-site displacement. Okay, this machine is recording both the things, the loads, the force as well as the displacement. I have written here the sigma, but actually I am again and again saying the force. Okay, so the force is measured by the load cell. This displacement is measured by the cross-site movement, but this is not correct. And due to that, the modulus of elasticity sigma by of strain is not correct. For that, what is required? For that, we need the extensometer. So what is this extensometer? Actually, extensometer is an external device which is having the strain rosette inside it, and with the help of that, this is the specimen actually. You can see this is the specimen. Okay, the shape and dimensions of the specimens, all of the things I will explain in the coming part. So if you will see, this is the extensometer. Okay, this extensometer we have placed on the specimen. It will measure the elongation in the specimen directly without the effect of any machine movement. The play between the screw and the crosshead will not count here. Either it is due to the screw driven or the hydraulic driven, or there is any uh, gap between the hole while putting these fixtures. Okay, nothing will affect because this strain rosette is directly put on the specimen. So that's the benefit of this extensometer. This is of Epsilon company extensometer, and this is a BIS company extensometer. Here you can see this is a dog bone shaped specimen. Okay, this is a dog bone shaped specimen, and we have kept the extensometer. This is the extensometer. The length between these two is always fixed. According to me, this may be of 25 mm of length. Okay, so 25 mm of length is there between at the gauge position, and how much it will get expanded will be recorded by this extensometer. Okay, so del I will directly get from this extensometer. The strain will be equals to del by of 25, whatever the gauge of this extensometer. Okay, either it is of 25, sometimes it is of 50 mm or 12 mm. It will be mentioned on the extensometer. So like this we can measure the strain. If we will know that strain, then what will be happen? We will get we have got the stress, that is force by area, and then now strain, that is displacement by of gauge length, and this gauge length we will directly get from the extensometer. Okay, it will come within a fixed gauge length. So from there we will get the slope E in the linear region. Okay, and this will be accurate. So that's why we need the extensometer. Whenever you need the modulus, we need the extensometer. Okay, the shapes of the samples and why. Actually, the shape of the samples, just we have seen in the last part, it is having the dog bone shape we have seen with the extensometer. So actually this shape and size will be decided by the ASTM. Whether it is a brittle material, ductile material or composite, what type of material is there, we will go and search in the ASTM. Okay, and from there we will get the size. Actually this size and the width, length, all things will be calculated by this ASTM with the some specific things. For example, the whether the stress concentration is generated there or not, or the what how it is failing between the gauge length. So all of that things they have took care, they take care actually this ASTM. Okay, so ASTM D3039 for this ASTM for composite material, ASTM D3039. Here I have took the table. Okay, and this table shows if we have the 0 degree composite material, we have made the laminate with the 0 degree unidirectional fibers. Okay, in that case the width is 15 mm, the overall length is 250, the thickness we can made 1 mm, and the tab length is 56. Means to say, what they want to say, the shape is, the shape can be rectangular. Okay, they are saying the overall length 250. In 250 the tab length is 56. 56, 56. Okay, this is the tab length, this is the 56, 56. Okay, the thickness is 1 mm, and the tab thickness, whatever the tab we are going to put here, so that is having the 1.5 mm of thickness. Okay, if we are using the 90 degree, if we are using 90 degree unidirectional composite, okay, the fiber will be in the transverse direction, or balanced or the symmetric or the random discontinuous. In that case the width is 25. In that case we have to increase the width. Okay, now just for the symbolically I have just increased the width. Okay, while for 90 degree the length has, overall length has decreased. For other case the two lengths are same, so just I am keeping the overall length same. And we have to increase the thickness also. We have to increase the thickness, that is 2.5 mm. Okay, the tab length they have not mentioned, but generally we are taking it of 50 mm. Okay, we are taking it of 50 mm on each side. As you will do the experiment you will understand it. Why the 50 mm? Because the when we are putting this sample into the grips, so grips are having the space available that is within the this range 50 mm, so that's easy to hold it. So you can see this all the thing, the size, shape, everything we are directly getting from the ASTM. Okay, and we will get the at what crosshead movement, at the crosshead or the position rate, or what position rate we have to do the testing. So all the testing speed is also mentioned in the ASTM. Okay, this is for the composite material. Similarly we can go and see the ASTM D638 for plastic materials. Here if you will go there, that will give us the dog bone shape. So why they are using the dog bone shapes, so that I am going to explain you. Then I will take you directly to the ASTM. Okay, just I am trying to make the dog bone shape. Okay, this part is not having a properly dog bone shape. Now it is a good. So why we are making this dog bone shapes? Okay, actually what will be happen if we will make a straight samples? If we have the straight rectangular samples, first what the problem we have, so that you should know what will occur, what will generally occur. This will be the cross sectional area, this part will be the tab length which will be held by the grips. Similarly here, this will be held by the grips. So this is the gauge length, this is the gauge length here, this will be the gauge length. What occur, what will occur when this part will be held by the grips? So while holding the grips, this cross section will get little bit get thinner. Okay, there will be some squeezing of the material, or the thickness will get reduced. What the overall thickness will be there, it may be 0.001, but it is lesser. And what the stresses value will be there, the stresses will be forced by of area, and that is the cross sectional area. Wherever the area will be the minimum, stresses will be the higher. Wherever the stresses will be more, the failure will occur at that position. And maximum times, if we will not, if we will going to use the same cross sectional area, so it will be generally fail near the grips. Okay, we don't want to fail it near the grips. Okay, because and what other things happen if we will going to increase the area like this. Instead of like this, we have made this cross sectional area. Okay, we have just said. So then what will occur if we will make the specimen like this? If we will make the specimen like this in the I section like type, then what will occur? In that case, there will be the, here the area is small, here the area will be the lesser, there high stress concentration will develop at the corners. It will fail at the corners. Okay, to avoid all of that situation, because we will in that case we will not know, come to know ki how the material fails, whether it will fail like this. Okay, the shape will be the cone shape, 45 degree. What the failure is there, we will not able to capture it. To capture the failure and to capture the exactly at the gauge between the gauge length, we are, and to avoid the stress concentration at the corners, we have made the dog bone shape. In dog bone shape also, what should be the radius, what is the gauge length, what is the overall length, that all the things are decided by the ASTM. They have done the so many testing, then they have find these things are better and is the best. Okay, so we can go and use that ASTM. Okay, just I'm going to show you the ASTM D638. D638. Okay, this ASTM D638 is used for tensile properties of plastics. This is for tensile testings of plastics. Okay, here we will go testing machine, everything we will come to know. Okay, test specimen, whether it is a sheet, plate, molded plastics. They will mention all the things, rigid and semi-rigid plastics, non-rigid plastics, reinforced composite. Okay, they have mentioned the different types, type 1, type 2, like this they have mentioned the different types. Now, I'm just directly came to here on the drawing. From here you can see that they are using the dog bone shapes. They have mentioned the gauge length G. Okay, they have mentioned the overall length. Okay, they have mentioned the width at the higher width. It is at the lower, it is width at the narrower cross section. Okay, they have meant, and you can come here. If you will come here, draw. If you will come here, okay, then you will come to know width. Width of the narrower cross section for the type 1 type of material, type 2 type of material, type 3, type 4. These all the things I have already just shown you before. Key whether it is the rigid plastic, which type of plastic, polymer plastics. Okay, according to that we can go see the type 1, type 2, type 3. And width of the narrow cross section, width overall, length overall, gauge length. Okay, for example I am just showing for the type 1. You can see here the width at the narrow section is the 13. This is the width is the 13 mm. Okay, width overall is 19 mm. Here the width is 19 mm. Okay, here the width is 19 mm. Okay, and what is the overall length? Overall length is 165. This is the overall length, that is the 165. And the gauge length, actually I am interested in the gauge length is 50 mm. This gauge length is the 50 mm. And what is the L? What is the L? If you will see, L is the 57. Actually when we make this the fillet radius, okay, this fillet radius will, when it will be come here and meet this straight lines, so at that time it will not completely straight, so they are given this length. So that's why it is just only 57 and the gauge length is 50. So this they have the at 3.5 and 3.5 to incorporate that things. Like this, we can come to know the dimensions directly from the ASTM. So just you should know which ASTM you have to use. For the tactile material, aluminum, the ASTM is different. They will come and tell you the failure reason, everything they will tell you. Okay, the procedure, how we are going to calculate the stress, strain, everything they will come and tell you. Okay, how to measure the stress, how to measure the E values. So they will come and tell you whole things. Okay, and after that, what is the speed of testing the material? Okay, so that's one of the important thing, and that you will get directly from the ASTM. Generally, for example, for the composite material, that is 1 mm per minute of cross head movement. Okay, and what about the failure position areas, whether it is acceptable or not? That is a very important. Okay, I have already explained you. If we have the sample with the dog bone shape, okay, just I made it a rough sample. If your samples get failed in the higher fillet areas or the where this radius is there, if the material is failed from there, means to say you have done some mistakes, because at the gauge, at the gauge length the area is lesser. It must fail somewhere near the gauge length. Okay, it must not fail here. When we have these steps, when we have the composite material, in the case of composite material, we know that these here are the tabs. So this material must not fail near the tabs. Yes, in if all the if we have make the 6 samples, if all 6 are failing near the tabs, means it's a material behavior. But if you from the 4 you have done the 6 testing, 4 are failed from somewhere here. Okay, fiber pull out is there in the composite material. Okay, or there will be some damage at 45 degree, and 2 samples are break at near the tabs, so we can't accept near the tabs. Okay, sometimes these tabs, when we are joining these tabs with the material with the help of some adhesive, generally we are using the bond tight. Okay, sometimes these tabs get failed, so we have not to accept that type of samples. So this is the basics things about the tensile testing. In the next video we will show you the tensile testing on the UTM.